Hello everyone. So let's begin with today's session for the mathematical methods in physics. So this is week 5 of the live interaction session. In this session, I'll be mainly discussing about about the concepts that were being discussed in the previous week, and also few of the problems that will help you solve the assignments for that was given in the previous week. So yeah, let me introduce myself. I'm Biju Shah. I'm a PMRF research fellow at Isaac Tirupati. So yeah, let's start with the today's session. Yeah. So to begin with, I would like to introduce this classification based on the differential equations. So differential equations can be broadly classified into two categories. One is the ordinary or the total differential equation, and the second category is the partial differential equation. So if I were to give an example of each category, then this is how the partial differentiation looks like. So mainly partial differential equation of a function if which is a function of two variables x and y. So the partial differential equation would be So this is an example of partial differential equation. So what you see here is f is a function of both x and y, but the derivatives are not with respect to both x and y at a time. It is being partially carried out either with respect to x, which is in the first term, and next term is the partial differentiation with respect to y, keeping x as constant. So the first term is differentiating with respect to x, keeping y constant, treating y as constant. It's not a variable, so we keep y as constant, and in the next term we keep x as constant and differentiate with respect to y. So that is the concept of partial differential equation. An example of ordinary and total differential equation would be suppose a function f is a function of only one variable, that is x, then the total differential equation would look like the total differential equation would look like del f df dx plus, let's say, f and some function of x. So this is how the an example of an ordinary differential equation is. So here we differentiate with respect to x, and it's not a partial derivative, so x is always considered as a variable. So that is the difference between the ordinary or the total differential equation with respect to partial differential equation. In this lecture we will mainly consider about this part of the differential equation, which is the ordinary or the total differential equation. So we see the ordinary and total differential equation can be sub-classified into various other categories. So one such category is the in terms of the linearity of the differential equation, and the other sub-classification is with respect to the order of the differential equation. Now what do we mean by linear differential equation, or what do we mean by the order of a differential equation, that will come across in subsequent slides. So the first on the terms of linearity, differential equation can be categorized as either linear ordinary differential equation or the non-linear ordinary differential equation. Similarly, with respect to order, it can be first order differential equation or higher order differential equation, that is second, third, or the higher order differential equation. So let us first study what is meant by linear ordinary differential equation. So linear ordinary differential equation can be of any order. So we can have a first order linear differential equation or the higher orders linear ordinary differential equation. So this is an example of a linear differential equation. So you have like a0y plus a1y dash, that is the first order differentiation, and the second order differentiation is contained in the third term a2y double dash. Similarly, other higher order terms equal to the on the RHS you have b. So the characterization of a linear differential equation is that your the coefficients to the higher order coefficients to the y or its differentiation, that is either y dash plus y double dash or higher orders, they are either constants or they are functions of x alone. Similarly, the b, the thing which appears on the right hand side or without any y or y dash, the b also is either constant or functions of x alone. So that is the characterization of linear ordinary differential equation. Yeah. So let us consider an example to judge whether a differential equation is linear or non-linear. So the first example goes as follows. So this is d square y dx square plus dy by dx plus y. So when we write this, when we compare this particular equation with this differential equation, what we see here is my coefficients of higher orders and the y terms, that is my a0. When I compare this with this, my a0 is equal to 1. This is my a0. Similarly, my a1 and a2 all are 1, and also my b is equal to 0. So we see that the coefficients are they are constant, so that would imply that it is a linear ordinary differential equation. Similarly, in the next question, what we see is my b, this is my b, and this is my a0, and this is my a1. So yeah, so let me repeat this particular section. So I just began with discussing about this classification of differential equations. So these are the two broad classification. Then there are other subclasses involved. So first of all, I started with discussing linear ordinary differential equation. So in that case, what we check is whether the coefficients are either constants or they're functions of x alone. So I was discussing about the very first example. So in this differential equation, when we compare with the prototype given by this, what we see is a0 is equal to 1 and a1 a2 both are equal to 1, and my b is equal to 0. So the requirement was that the coefficients and the b part has to be either constant or functions of x alone. So yeah, since they are constant, we can conclude that it's a linear ordinary differential equation. Similarly, for the next differential equation, what we see is the b part is equal to sine x, and a0 is equal to my x, and a1 is equal to x square. So what we see is that all of them are functions of x. So the requirement was that they can be either constant or functions of x. Since we see they are functions of x alone, so we conclude this particular equation is also linear ordinary differential equation. Now let us look into a category of non-linear ordinary differential equation. So when you compare this equation with this equation, the left hand side is same, but the difference occurs on the right hand side. So on the right hand side, what we have is b. So my b is no more just a function of x alone. So b is now a function of y, which was the dependent variable. So since the right hand side is a function of dependent variable, so we conclude that it is not a linear differential equation. But since in this particular problem, my right hand side was a function of x, that was my independent variable, so it was a linear differential equation. But this particular example is non-linear. Yeah. Same thing, the the form of the linear differential equation can be written in terms of in term of operator. So far we know what an operator is. So the operator acts on an unknown function and it spits out a function. So the linear operator L acts on the function which is y of x, and it gives a function f of x. So if the functions it gives is independent of y, so that would conclude that my operator L is a linear differential operator. So almost we have the same definition, but we have expressed in terms of operator. Yeah. Now let us come to the special cases of this differential equation. One thing is that if my function f is equal to 0, then we can consider that to be a homogeneous equation. If f is not equal to 0, that is inhomogeneous category. And one very important property of linear differential equation is that, suppose your linear differential equation has two solutions given by y1 and y2. Then any linear combinations of them, let's take a linear combination of y1 and y2, that is alpha y1 plus beta y2. Then the linear combination is also a solution of the ordinary differential equation. So we had two solutions given as y1 and y2. A linear combination of them is also a solution of the ordinary differential equation. That happens because the differential equation was a linear operation. Had it been a non-linear operation, we would not have concluded this. So that is something which is known as superposition principle, which often we come across in physics. Now, since I started with the classification given as this, so far I have discussed these two categories, linear ordinary differential equation and non-linear. Now let me come to the classification based on the order. So this classification is based on the order. So what is meant by order of a differential equation? So the order of ordinary differential equation is the the order of the highest derivative that appears in the differential equation. So this is a very general form. So we have, first of all, the first term is nth derivative of y with respect to x, then n minus 1th derivative of y with respect to x, and so on, equal to bx. So see, all of these are functions of x. So we can conclude that this is a linear differential equation. That is like one exercise you can think, like had b was written as a function of y, then it would no longer be linear, then we would have called it as non-linear. But this particular example is a linear differential equation. So now what is the order? So the order of it is the highest. What is the order of the highest derivative? So the highest derivative here occurs is in this place. So provided your coefficient is not equal to 0. If it was equal to 0, then that would vanish. So the existing highest derivative would be n minus 1. But if the coefficient is not equal to 0, then the order is equal to n, the highest appearing derivative, highest order of the highest appearing derivative. Yeah. So the first order ordinary differential equation, we can consider this to be a general form. So this is the highest order appearing, and it has the order equal to 1. So here n is equal to 1. Yeah. Now see, to impose further, like this is a very general form. It can be either linear or non-linear. So a subclass of this would be linear first order differential equation. What we can call this as linear first order differential equation. So let us look at each term. Linear because my a0, so this is my a1, this is my a0, and this is my b. So all of them are either constant or functions of x alone. So that makes it linear. Now let us come to the first order statement. So here the order of the highest appearing derivative is 1. N is equal to 1. So yeah, that makes it the differential equation to be linear first order differential equation. Now let us come to a question, a very simple question is to check whether the following ordinary differential equations are linear or non-linear. Yeah. So let us look at each question. So what we see in the first example is in this particular first example, this is my B part and this is my A0. So this is my A0 term, this the appearing with y square, and this is my A1 term. So you see the other nonlinearity factor that comes from is my y being written to the power of 2. So had this been something like dy by dx plus xy equal to 2x, then I could have claimed it to be linear. But now my y carries a higher power, that is y square. That makes this equation non-linear. There is another. This is another possibility of the equation to be non-linear. So my first equation is non-linear. The second equation, when you see, this is my b and it is a function of x alone, and my a0 is equal to -1 and this is a2 is equal to 10. So what we see from b, since they are all either constant or functions of x alone, so it is linear. Similarly, you can also speak about one C, what it is like. Can you please unmute and answer according to what you've learned so far? Yeah, I can give you hint, like this part you see, this is b part. So this, what the requirement was, b to be is to be the function of x alone, but since here you see b is function of y, so that immediately confirms that this is a non-linear equation. Now let us look at the D part. So in D part, what you see is this is my A0, sorry, this is my A2, it is 1, and this is my A1 equal to x, and A0 is equal to 1. So yeah, so that is, this equation is linear. So we had two linear differential equation, which is my example B and D, and two non-linear, which is example A and C. So I hope that part is clear. Now let's move to how to find the order of the ordinary differential equation. So one thing, like the ordinary differential equation, because the derivatives are with a total derivative, like you see d dx, so there is something called partial differential equation where the derivatives appears as like this form del x. So in this particular case, so your function f is a function of, let's say, more than one variable x and y. So the process is that, suppose if you come across an equation like differential equation like this, so in the first term the y is held constant and it is partially like differentiated with respect to x, and in the second term x is kept constant and differentiated with respect to y. So But this all these problems which we'll be discussing in today's class, it's mainly it's all ordinary differential equation. So let's find the order of this ordinary differential equation. So the ordinary differential equation from the first problem, the highest order of the derivative is 3. So that is the order of the differential equation. So can you guess the order of the next question? So the highest order derivative is in the first term itself. So n is equal to 1. So yeah, absolutely correct. Yeah. So here what you call, this is your first order differential equation. Now, like, also it's not actually mentioned in the question, but since you have checked if equation is linear or non-linear, you have learned to check it. So you can also see, like, for this particular equation. So what do you see? Like, there is a very important catch here, that there is higher powers involved in the derivative itself. So any higher powers involved in the derivative or in the dependent variable, like either y to the power 4, y is my dependent variable, or dy by dx being raised to power 4. So any higher powers appearing in the differential equation would make the differential equation non-linear. So we will conclude that this is my non-linear differential equation. And in the second question, so yeah, can you please write, like, either speak out or write in the chat box what about the linearity or non-linearity of the second question. Yeah, so this is absolutely correct. So this is first order linear ordinary differential equation. Yeah, so like late in the for most of the time we will be discussing about this first order linear differential equation, how to solve them, and mainly towards the end I will discuss about first I will discuss about this first order linear ordinary differential equation most of the time, and in the later part of the class I will introduce this how to solve the second order linear differential equation. Yeah. So even before going towards the main content of today's lecture, let me also familiarize to you something known as orthogonal trajectories. So let's say that C and C dash are families of curve. So every curve can be represented as an equation. So if it's a planar curve, we can represent with y as a function of x. That would represent a curve. So let's take a straight line. So yx equal to mx plus c. So this is a curve, and it is called as family of curves because you're free to choose m or the value of c to be anything and get a large number of straight lines. So that would represent a family of curves. Similarly, C and C dash are families of curves, but if they are supposed to be orthogonal, then they have to follow this particular relation, that is the slope of the curve. This is the slope of the curve C, and this is the slope of the curve C dash. So they are to be connected through this relation. If they're connected through this relation, then the curves are orthogonal to each other. So let us find, so we have a family of curves which are given by this xy equal to c. So let's find the orthogonal trajectories of the family of curves represented by this. So the first step would be to find the slope of this. So the slope of this would be given by dy by dx. So let's differentiate. So we have xy equal to c. So when we differentiate with respect to x, we get y plus this is for the curve, this xy equal to c, this is for this curve. So okay, let me name something different because we have already c. So this is a family of curve A, let's say, and this is the slope given of that family of curve. So we have to find another curve which is another family of curve which is orthogonal to this. Okay, so the another family of curves which is orthogonal to this B A dash. So its slope is -1 by the slope of this. Sorry, what? Yeah, exactly. Yeah, means you are saying the slope of this curve, right? Yeah, the other family of curve. Did you write a slope equal to x by y, because but it is coming out to minus x? Yeah, x by y. Yeah, yeah. So this is the slope of the other curve. So let us get to the equation of this. Ultimately, you have to represent it in the form of equation. So what we have is dy by dx equal to x by y. So now let us solve this differential equation. So let's cross multiply. This is something called variable separation. So we have separated y with on the one side and the x on the other side. Now let's integrate both sides. Yeah. Yeah. So this is the definition of A dash family of curves. So we have actually found out a family of curves which is orthogonal to A, represented by xy equal to c. Yeah. So again, the next after having discussed about the orthogonal trajectories and all, let's come to this exact differential equation. So for a differential equation, if it has to be exact, then this relation has to be satisfied. So my differential equation is written in this form. So I have m dx and n dy, and m and n are functions of x and y. Yeah. So if the differential equation is exact, then my del m by del y is equal to del n by del x. Now this is a partial derivative, okay, because see, m is function of both x and y. Similarly, n is also a function of x and y. So you take the partial derivative with respect to y of m, and then see if it is equal to the partial derivative of x, a partial derivative of n with respect to x, keeping y as constant. If they turn out to be equal, then the differential equation is exact. Yeah. So let us check whether the given differential equation is exact or not. Okay. So comparing this particular form with this, yeah, this is my m and my n is now. To check if it is exact, let me find out that is del m by del y. Yeah. So taking partial derivative means x constant, so the first term is no longer appearing. So it is 6x square y minus 6x y square. So since you see my So we have del m by del y is equal to del n by del x. Therefore, the differential equation is exact. Let us come to the next question. So in the next question, you have form given by this. Let me copy this. Yeah. So here m is given by this. Yeah. So ex by y and then minus, sorry, minus of, yeah. So here it is, write this particular thing, ex by y minus x by y, so here it is e x by y and it is 1 by y, and okay, sorry, this supposed to be this itself. Okay, so this part and this part cancels. Okay, so we have del m by del y equal to del n by del x. Therefore, the equation is exact. So this is how to check whether differential equation is exact or not. Yeah. So let me again come back to the linear first order differential equation. So this is how the linear first order differential equation in general looks like. So this is inhomogeneous. Inhomogeneous because this qx is not necessarily 0. So that makes it inhomogeneous differential equation. So the solution for this differential equation is given by this. So I have y multiplied with something known as I. So I is my something called as integrating factor. So okay, integrating factor is equal to exponential raised to the power of integration px dx. So the term which occurs here, we integrate it with respect to dx, and that is kept as in the power of the exponential. So that is something which is known as integrating factor. I have represented it with I. So y into I is equal to integration of qx I dx plus some constant of integration. Okay, so let me proceed towards applying this formula to solve this differential equation. So when you compare, okay, so first of all let me compare this differential equation . So you have px to be equal to 2 by sine x, and your qx is equal to tan cube x by 2 by sine x. So this is, when you compare, this is your p and q. So the first step is to go towards finding the integrating factor, which is I. Is exponential px So this can be written as just tan square x by 2. So this is your integrating factor. Now let us write it. Tan square x by 2 is equal to integration of tan square x by 2. Then you have qx. So in this case my qx is equal to tan cube x by 2 by sine x. Plus c. Yeah. So you can actually replace sine x with 2 sine x by 2 cos x by 2. So after you do this, so like you can cancel this, like you have this tan x, so you can write tan x to be tan square x to be something tan x by 2 from one part, and sine x by 2 cos x by 2. So this sine x and this sine x cancels. So what you're left with is this in the numerator and then 2 cos square x by 2. Yeah. So it's 6 square so let us focus on this integration. Okay, this particular integration. In this you can take tan x by 2 to be equal to some variable, let's say t, then your dt by dx would be equal to sec square x by 2. So dt is equal to sec square x by 2 by into dx. So what you have is t to the power 4 Yeah, and there is a 2 coming because dt by dx equal to 1 by 2. dt by dx and then 2 dt. It is 2 by 5, tan 5 of x by 2. Yeah. Now let me write it here itself, like y is equal to y tan square x by 2 is equal to 2, and this 2 and this 2 cancels. So what you have is 1 by 5 10 to the power 5 of x by 2 plus c. Yeah. So this is how we used this particular formula. So given an inhomogeneous linear differential equation, we used that particular formula and could arrive at a solution of that. Yeah. Now let me introduce something which is known as Wronskian of a function. So suppose you have some n number of functions which are given by this, like f1x, f2x till fnx are the n number of functions. So if the Wronskian of those set of functions comes out to be non-zero, then the functions are said to be linearly independent. So linear independence we have discussed in the the linear algebra classes. So this is another way of checking the linear independence of a set of functions. So what is done here basically is you form a matrix, n cross n matrix, with the first row given by the functions itself, and the remaining rows are the the derivatives, the successive derivatives, like the first derivative and the second order derivative, and last row is the n minus 1th derivative. So if the determinant of that particular matrix comes out to be non-zero, then this set of functions are linearly independent. So let me directly go to a problem which applies this. So we have to check whether this set of functions are linearly independent or not by the method of Wronskian. So my matrix would be, it would be a 3 cross 3 matrix. This is the second row is the first order derivative, which is 0, then 1, which is cos x. Let's expand along the first column itself. So when we do that, we have 1 cos x, 0 minus sin x. Yeah, it came out to be minus sin x. So so it is not 0, so it's not identical to 0. Maybe at some particular value of x it comes out to be 0, like at x equal to n pi categories, this particular determinant is 0. But for any general value of x, Wronskian is not equal to 0. So that would imply that these sets of functions, that is 1, x and sin x, are linearly independent. And you can also check by the other methods we did in linear algebra classes, that you can write it as a linear combination and set it equal to 0. So given that they are linearly independent, the coefficients also had to be, all the coefficients had to be 0. So by that method also you can check they are linearly independent. Now let us come to a some special category of first order differential equation. So this is a Bernoulli equation, something known as Bernoulli equation. So when you compare, like you can easily compare this set of like this particular differential equation with what we saw in the earlier just few minutes ago, which we saw here. So when you compare this, just for the sake of comparison, I am bringing it to that slide. Later I will delete. Yeah. So just for the sake of comparison, what you see is, like I already mentioned, this was my linear first order differential equation, fine, because like this b is a function of x alone, and a0 and a1 both are functions of either constant or function of x. So what do you think, like this particular equation, is it linear or non-linear? So difference is on the right hand side. I can pointing it out for you. Difference is on the right hand side. So what do you think, like the Bernoulli equation, is it linear or non-linear? Yeah, it's correct. It's absolutely correct. So this is non-linear. Non-linear because there is a term called y raised to the power n. So that is what makes the difference. So this particular equation is non-linear. So it's a non-linear first order ordinary differential equation. Yeah, but we will kind of try to manipulate and make it look like linear, and then proceed with the usual method of solving. So the way to go about this is, so this particular equation is turned out to be non-linear. So what you do is make a substitution. So you change the form of dependent variable. So earlier my dependent variable was y. That was my dependent variable. Now make it to be z, which is equal to y raised to the power of 1 minus n. So the power n which appeared here, take 1 minus n and make a change of variable where z is equal to y raised to the power 1 minus n. So when you substitute that particular value here, in this particular like equation, replace everywhere where y appears with this, and also take the derivative, like what dy by dx would mean in terms of z. You can easily do it, and ultimately the form looks like this. So this particular equation is independent of y, does not carries explicitly any y, but there is dependence of y because z is depending on y, but explicitly it does not depend on y. So now your like differential equation is linear because this thing is just a function of x, and also this thing just a function of x, and your dependent variable is z. So by the expense of making change of variable, you have reduced a non-linear differential equation to a linear differential equation. So that is something which you achieved, and it will help you a lot to solve the question. So let's quickly go to this particular equation to solve this. So rewriting this, I am rewriting this in a form which is identical to the earlier. So I have minus cos theta drt theta plus r sin theta equal to r square. Yeah. So like in this particular problem, your independent variable is theta and your dependent is r. Clearly this is non-linear because this term involves r square, so that makes it non-linear. So now how to solve this? So when you compare this, what you see, your n which appeared here is Yeah, here n is equal to 2. So let me recast this equation into this form. So necessary change in variable is you have to make some z equal to y to the power 1 minus n. So here z is equal to r to the power of 1 minus 2. Yeah. So you make this change of variable z equal to 1 by r. So the next, so the linear form in z would look like dz by d theta, since my theta is the independent variable here, plus 1 minus n, so 1 minus 2 p. Okay, so in this case my p was this, including the minus. Yeah. So this is my p and this is my q. Yeah. Again, 1 minus n is basically minus of 1 and minus r square cos theta, that is essentially yeah. Oh, sorry, my r itself like it involves r square, so it has to be minus of cos theta, so the entire thing is not my q. It is minus 1 by cos theta, minus of sec theta is my q. Yeah. So from here what you see, so let me rewrite this particular equation in a more simpler way. So it would be like plus tan theta z to sec theta. So here in this the dependent variable is z and the independent is theta itself. So now this is a linear equation. So linear equation. Now easily you can solve this by the method of using the finding out the integrating factor, which is exponential of integration of tan theta. You can easily do it, and you can use that whatever you get after integrating. So I'm not integrating it out, so simple integration. So z into the integration you get, yeah. So this is a solution for z. But remember, my z was equal to 1 by r. Ultimately, your equation is in terms of r. So replace your z with 1 by r. In the very last step, replace z with 1 by r. Yeah. So you can complete these integrations later, like this is mainly a very simple integration. So the main motivation behind doing this problem is to make a change of variable and reduce a non-linear equation into a linear equation and then solve it. So we have achieved that. So I hope that's clear. So let me go to the next topic, which is something known as homogeneous function. So this homogeneity of a function, it means that suppose if you have a function f of xy, so let's take a function of two variables x and y. Yeah, your f is a function of two variable. So if that function can be represented in this form, if a function can be represented into, so then you can conclude that your function is homogeneous and its degree is n. So let's quickly go towards finding the homogeneity of this particular two function. Yeah. So let's take x. X squared to be common, and then we have yeah. So we started with this function f, and let's yeah. We started with the function f, and we could recast it into this form, that is x to the power n f of y minus y by x. So that would say that my degree is 2 because n is basically 2. Yeah. So we have proved that this is a homogeneous function with degree 2. Now let me go to the next question, where it says that we have to prove that they are not homogeneous. Okay, so let's start with the first function, x square plus y. Yeah, so here essentially the function is basically a function of y by x square. It's not y by x alone. So this is not a homogeneous function. But had this been just x plus y, then it would have been a homogeneous function with degree 1. But this is not a homogeneous function. So the next question is x plus cos y. Yeah. Clearly this can never be a homogeneous function because the cos is just a function of y. The x can't be, we can't write it in a form of like y by x. So this is also not homogeneous. So if I were to just take x common, and it would have the form, yeah. Similarly, y plus 1 can also be like seen that is not a homogeneous function. So yeah, so we have learned about the homogeneous function. Now let me go, like if the coefficients that appear in the differential equation turns out to be homogeneous function, so there is an easy method and quick method to solve it. So given this is a differential equation, so what you see here is a differential equation p dx plus q dy equal to 0. So provided like p and q are homogeneous function and of the same degree, so the n that appeared here is a degree. So if your p and q are homogeneous function of the same degree, you can solve this particular differential equation by making this substitution, that is y equal to x into v. So when you do this substitution, you can easily separate the two variables on the two sides of the equality. So the left hand side would comprise of just y and the right hand side would comprise of just x. So you have achieved separation of variable. Now next step is to just integrate on both sides and get the solution. Yeah. So let us do that particular method for this particular differential equation. Yeah. So I would like to like I would like to request you to say me what is the degree for the p and q that appears in this equation. So if I were to modify this, my okay, let me say p is here. So yeah. So p is the coefficient of x. So in this case my p is minus of 3y square minus of 2xy. So that is my p. Okay. So yeah. Wait. 2xy plus x. Yeah. Similarly, here also you can write it in some form x square f of x by y. So yeah, you're correct that degree of the functions are 2. So they are same. They have the same degree and they're homogeneous. So let's go towards applying that process. Okay. So what we have to do is we make a substitution. So y into x, y is equal to x into v. So with that substitution, my dy by dx becomes yeah. So wait, we had this particular equation. Yeah. Yeah, this is how the equation was. So now I have obtained my dy by dx to be this. So let's me substitute that. So substituting, what we get is v plus x dv dx and also let me put v wherever y appears. So with that change, this particular right hand side would be, so it would be 3 y square, so it is x square v square plus 2 vx square 2 vx square plus x square. So that is equal to 3v square. Okay, so the x squares are common. Yeah. So now we have written our equation with two variables v and x. Let's bring v to this side. So I have Yeah, so I have v square plus 2v, yeah, v minus v, so it's just v. Yeah. So now easily you can separate it out. So basically you have 2v plus 1 v square by v square plus v dv and dx by x. So you have separated out both the variables in the two sides. So let's integrate. Now the next step is to integrate. So here is log x plus constant. So this is a easy integration. So you just put t is equal to v square plus v. So dt by dv would be 2v plus 1. So dt is my dv, 2v plus 1 dv. So even on the right hand side I have ln of v square plus v. Yeah. So we can actually make some like choose some constant and write it as to be ln of c. So that would make everything to be like without exponential. So v square plus v is equal to c of x. So my v was actually y by x. So yeah, so this is what my solution to the differential equation is. Yeah. So what we did is like we checked for the homogeneity and they are of the same degree. You already said that their degree equal to 2. So the next step was to make us like some change in a variable. So we substituted y equal to xv and then we could separate out the variables on the two sides of the equality sign, and then we could integrate and then resubstitute my original variable and arrive at the solution. So all this was regarding my first order differential equation. So see, everywhere the highest order of the differentiation was 1. So everywhere you came across dy by dx. So having discussed so much about the first order differential equation, I think let's move to the second order differential equation. So the second order homogeneous linear equations, and the constant is with constant coefficient. So let us understand term by term what does this mean. Second order because this term appears here. The highest order is 2. The derivative, highest order of the derivative is 2. So n is equal to 2. And the next was homogeneous. Homogeneous, remember, because like very beginning I said if you write an operator, a differential operator in terms like it's a differential equation in terms of operator, then L of y is equal to can be written as L of y is giving you fx. So if your fx is 0, so the differential equation is homogeneous. So you see directly here f of x equal to 0. So that is why it's a homogeneous. So the linear equation because a0, a1 and a2 are constant coefficients. So that makes it linear. So let us go about how to solve this second order differential equation. So the method is to like write an equation which is known as auxiliary, something known as auxiliary equation. So this is what is known as the auxiliary equation. Yeah. So your d is an operator, so it's first d dx is the operator. So we write this particular equation in terms of this operator form, and the next step is to find a solution of this particular equation which is known as the auxiliary equation. So having obtained having obtained the roots of the auxiliary equation, so the roots of this auxiliary equation is a and b are the roots of the auxiliary equation. So if the roots are distinct, okay, so if a is not equal to b, so the solution would be given as this: a e to the power ax plus capital B e to the power bx. So there are two unknown constant because the differential equation is second order. So far all the earlier cases we saw the unknown constant was 1 in number because the differential equation was first order. So depending upon the order of the differential equation, you get as many number of unknown constant. So capital A, capital B are your two unknown constants, unknown coefficients. So and A and B are the solution of the auxiliary equation. Now the next category is if the roots are equal. So if your A is equal to B, so this is how the equation, like the solution would look like. Now the next category is the roots are complex conjugate pairs. So in that case, suppose your root is alpha plus minus I beta. So the real part is alpha and imaginary part is beta. So you can write your like the solution either in this form or this form. So the real part appears in terms of the real exponential e to the power alpha x, and the imaginary part of the root appears in the e to the power I beta x. The beta is the imaginary part. Since using the Euler form we can represent it in terms of this cos and sine, so what we can do is we can replace e to the power I beta x in terms of cos and sine and can write it as this form. So these are the two three solutions that you can get depending upon the roots of the auxiliary equation. Yeah, so let us go about solving this particular second order differential equation. Yeah. So when you write in terms of let's say this operator, that is d is equal to d by dx, so that time you have yeah, so d is d dx, so you have d square y plus 4 . So now your auxiliary, how to solve your auxiliary equation is, can you say me the roots of the auxiliary equation quickly? Like basically you have to solve this. Yeah, basically you have to solve this equation, and the roots are the roots of the auxiliary equation. So, and also say me which category it belongs to. Like I have said that there are three cases. So are the roots equal? Yeah. Yeah. Yeah, they are absolutely correct. They are equal roots, and these are the two roots. So that says this particular problem belongs to this case 2. Yeah. So this is the solution of the differential equation. Yeah. Now also let us use this information to extract some knowledge about the coefficient. So what you have is at x equal to 5, the y value is 0. So 0 is equal to x equal to 1 by 5. So it is 1 by 5. Yeah. So you obtain your b is equal to minus 5a. So let's just put, so mm, yeah, b is equal to minus 5a. I've taken a common, x minus 5. X plus b. Okay, sorry, it's supposed to be this, right? Okay. So b is equal to minus 5 by a. Okay, sorry for this mistakes. So it is a by 5 minus b. Yeah, okay. So it's a equal to minus 5b basically. So yeah, let me put it again. So y is equal to so b common. Yeah. So this is the solution for this differential equation. So at the end what we did is we put a given condition. So this is this can be this particular initial condition. So since we have one initial condition, we could extract information about one unknown variable. So right now my solution is having one unknown variable, that is b. So this is how the, yeah, correct. B is equal to, yes, yes, thank you. Yeah. Now let's come to this next question, which is also based on this earlier concept. So you can also like solve along with me and say what is the, you know, the auxiliary roots and which category it belongs to. Okay, so directly I'm writing it. So it is 4d plus 5 no, actually it's this. Like I think because it's 2 and 2 cancels. So yeah, you're almost correct. Just this part. So the main thing is these are roots are. Yeah. So, yeah, so the roots are complex conjugate pairs. So that would mean that my this form is valid. So case 3 is valid. Yeah. Before that, let's. So what are the real and imaginary parts? So alpha was my real part, and sorry, this would be like beta x somewhere. Yeah. So beta was my imaginary part. Okay. So in this case, my real and imaginary parts, like real part, that is alpha, is equal to my minus 2. Okay. And the imaginary part is equal to also it's equal to 1. So it's equal to 1. So from here we got to know. So my solution is e to the power of minus 2x yeah. Okay. So this is my solution, but it is a general solution because there are two unknown constants. So let us use these two statements and get the values of a and b. So y is equal to 2 and okay. So when x is equal to 0, so when x is equal to 0, your y is equal to 2. Okay. So that means that x equal to 0 means the only thing that would remain is my a. So you get this from the first condition. So rewriting your equation, let's yeah. And the next condition was okay, dy by dx would be minus 2n yeah. Dy by dx at x equal to 0 we have to find. So in that case we have minus 2, and then we have this 2, and then we have plus b. So this is what is b minus 4. So d square y by dx square. So that would be minus plus of 4 e to the power minus 2x, and 2 cos x plus b sin x remains as it is, then minus 2x. So in this case you have and here also you have minus, okay, yeah. So at x equal to 0, what is that? We have to find that. So at x equal to 0, so it's 4, and then you have 2 from the first term, and then you have minus 2 b minus 2 b, and it is minus 2. So basically you have 6 minus 4b. Yeah. So since they are said to be equal as one of the condition, so 6 minus 4b is equal to b minus 4. Yeah. 10 is equal to 5b, so b is equal to 2. Sorry, b is equal to 2. So a is equal to 2 and b is also equal to 2. So basically you have y is equal to 2, taking out in common e to the power minus 2x cos x plus sin x. Yeah. So this is the solution. So this contains no unknown constant. So basically you know both a and b by using the initial conditions. I hope this is clear. Now let us look at, I think like I have two such general equations. So this is equation which the form does not look like similar to any of the form we have discussed so far, but by some kind of manipulation, like some intelligent guess, we can actually reduce it down to the form which we already have studied. So let's start with this discussion. So yeah. So for this problem, you see the higher order, that is dy by dx to the power square, is a term which makes it non-linear. So this is a non-linear differential equation. So in order to remove the non-linearity, let us with that motivation, so let us take let us take dy by dx is equal to some variable, let's say p. Okay, so your d square y by dx square would be dp dx. So now the equation looks like you have x dp dx x p square minus p is equal to 0. Now you can try to reduce into form that something which you already studied. Like let's try to make it into linearized form. Okay, so this looks like yeah. So still it is non-linear, because you see p square appears here. So in this case my dependent variable has become p, and independent variable is x itself. So this is the case of Bernoulli equation, like we already discussed. So now we have come to our comfort area. So we have studied how to solve Bernoulli equation, so easily we can use that technique to solve this particular equation. So comparing with the Bernoulli equation, the form of it was this was the form. So let me replace, since my dependent variable is p, to not get confused, so let's not get confused in this P and this P. Yeah. So my dependent variable is now P. So my N from here, what it turns out to be is 2, and Q is -1, and P is -1 by X. So this is the prescription you have in hand. So remember, let me go back to this Bernoulli equation, the form for this. Yeah. Yeah. So yeah, let us look here. So first of all, we have determined what are P and Q, and then we have to substitute this Z, that is in my case it right now it is P, to be equal to, sorry, like the Z is equal to, like so we are moving from P, that is 1 minus N, to something say Z. Okay, and your N is 2 basically here. Yeah, so Z is equal to 1 by P. So your N is 2, so here it would be 2, and your Q is -1, and your P is -1 by X. So what you have essentially is yeah, so this is the form you have. Now this is clearly a linear equation, right? This is a linear equation. So again, coming back to the method of, since we have moved from a nonlinear to linear by using the Bernoulli equation format, and right now the job is to find the integrating factor. So the integrating factor is it turns out to be X. So Y into the integrating factor into Q. So Q is 1 here. Okay, from this equation you have 1. Yeah. Okay, sorry, this is Z basically. Okay, Zx x squared by 2 plus C. Yeah, so what we got is Z is equal to x by 2 plus C by X. This is my Z, but remember Z is equal to 1 by P. Okay, so 1 by P is equal to x by 2 plus C by X. Z is equal to 1 by P. And also remember my P was dy by dx. So 1 by P is dx by dy. Because my aim is to ultimately find y as a function of x, right? So the next step would be easily to separate out the variable, okay? Because we have x by 2 plus c by x on one side, and then dy, and integrating both sides. So you can like later carry out this integration. So this is just a matter of carrying out this integration. So on the right hand side you have y. So this is how you can like arrive at the solution of a differential equation. So the key point in this differential equation, you had something like dy by dx to the power square. So anyhow you have to reduce it down to your known format. So the first intelligent guess would be to replace dy by dx equal to p. Make it not look like derivative, but make it look like a variable. Okay, so for the time being, let's say dy by dx equal to p. So having said that, we have reduced, like modified my form, and after modifying we discovered that okay, this particular modified form looks like the Bernoulli equation, which we already discussed. So then we again employ the techniques of the Bernoulli equation and then reduce it down to a form of linear equation. So right now we have moved to a linear equation which can be easily be solved. And once we achieve the solution of the linear equation, we can go backwards, like make the backward substitution of the variables and ultimately arrive at this form. So the job was to find y as a function of yx. We achieved that. So I hope that is clear. So yeah, now let me consider one last question, which is also a general method. So this is also something was discussed in your lecture. So provided you know a solution of a differential equation. So right now I have this differential equation and I know the solution of one of the solutions. So this is a second order differential equation. So you have two solutions, but you have known that one of the solution is represented by x. Okay, so one of the solution is just x. So using this knowledge, let us find out what is the other solution. Okay. So it was discussed in the lecture itself, like to go about solving this is to write y as a product of u and v. So in this case my u is known to be one solution, so that is y is equal to vx. So once we know what is v, we can easily get what is my y. So the main task would be now to know, aim is to know v. What is the form of v? Yeah, so again, since there are second order derivatives involved, so first of all, the first order dy by dx would be, so it is v plus x dv dx. Now carrying out again next derivative is okay. So my equation has this form, so it's x cube into this derivative plus x y dash, so it is mainly v plus minus of y, which is vx. Yeah. So from here you have then you have this this thing can be written as yeah. So again, let me try to reduce to a form which is known. So some we are trying to make it into a first order. Okay, so that would mean that so if I can substitute dv dx as some variable, let's say k, then my d square v dx square would be simply dk dx. Okay, so if I can make this change, then your form changes to something like yeah. So now this is a very simple, we have reduced it down to a very simple form, like we can easily make the change like the variable separation, then yeah. Now integrating both sides, yeah. So k is basically exponential of ln c by x square plus 1 by x. And remember what was my k? It was dv dx. So this is dv dx. So your v would be exponential of ln c by x square plus 1 by x dx, carrying out the integration. So what is it like? You have exponential of ln c by x square on one side, and like product this two products. So basically this is c x to the power minus 2, and here e to the power 1 by x dx. So you can carry out this integration. So mainly you'll apply integration of by product rule, and what you come across is yeah. So this is the final form. This is a new integration variable that comes because we are integrating this particular thing. So right now this is your v. So that is what it was, like one of the function, but other function was known to be x. So we have known v right now. The other function was x. So y is equal to x into minus c 1 by x plus c bar, minus c e to the power 1 by x plus c bar. So that is basically yeah. So in a neat form I could write this as so this is my solution so of the yx, the other solution, provided I knew one solution. So this was one of the solution. This is the other solution. So the x solution is something which you already was given. This is the solution we found. So linear combination of them is the total solution. I hope that is clear. So let me give a brief before, if you have any doubt you can clearly interrupt and ask me right now. Also in the process I'll give you a quick review of what it was done. So mainly I classified differential equation into two categories. One is the total or the ordinary, and the other is the partial differential equation. So this is an example of a partial differential equation, and this is a format of the ordinary differential equation. The change is in this is a partial derivative and this is a total derivative. And other, like even the ordinary differential, since in this lecture I may like focused on the ordinary differential equation, so the ordinary differential equation can be classified into two categories, the linear ODE and the non-linear ODE. And in terms of order, either the first order differential equation or the higher order like 2, 3, 4 and so on. So this is how the linear ordinary differential equation format looks like. So the a's and b's are either constants or functions of x alone. So some examples of linear and the non-linear ordinary differential equation, and also the when can we consider the differential equation to be homogeneous or not inhomogeneous. An important like principle called superposition principle. So if my y1 and y2x are both solution, then the linear combination is also solution of the differential equation. This is because the linearity of the differential equation. And the order is something that we discussed. So we also found out worked out few examples to check the linearity and also found out the order. So then also something we discussed about the orthogonal trajectories. So I introduced an example, a problem where I had a family of curve represented at x, y equal to c. Then we worked out and found out what is the family of curve which is orthogonal to this particular family. Yeah. So then the exact differential equation, this is the criteria that has to be that if this criteria is obeyed, then the differential equation is said to be exact. Yeah. So then we worked out few problems based up to find out the exactness of the differential equation. Then we started with solving the linear first order differential equation. So this is how we solved. We went on to solve, we found the integrating factor and so on, and went on to solve the differential equation. And then the next problem was next topic was using the Wronskian to know the linear independence of the set of function. So we had a set of function, then we calculate the Wronskian. If it came out to be non-zero, the determinant of the Wronskian matrix came out to be non-zero, then we claimed that they are linearly independent. Then some special category of first order differential equation, the Bernoulli equation. Yeah. And something also we discussed, homogeneous function. And then the very next topic was homogeneous equation. So in this basically, so if the two functions are homogeneous and they have the same degree, so then we could make proper substitution and can easily achieve separation of variable method to solve the differential equation. So we worked out one such problem. Yeah. And then next we move to the second order homogeneous linear equation. So far we discussed first order. In the second order we just discuss about this particular case where we would reframe our equation in terms of this operator method, like using the d is equal to dtx. In that operator we could rewrite this equation in this form and then achieve the roots of the equation. So depending upon the roots, if they are distinct root, equal root, or they appear in complex conjugate pairs, we have three cases and each solutions are different. So we worked out with two such cases. So mainly the first case was equal roots, case 2, and the next case was imaginary, they appear in complex conjugate pairs. So we also solved that. And then we came to some special category of differential equation where it does not exactly fit into our format which we learned, but we used some intelligent cases and tried to bring it down to the form which we know. So that was with these two particular problems. Yeah, and yeah, that was with the one that question problem, and the next problem was provided given that you have a solution of a differential equation, one solution, find out what is the other solution. So we found it out and we wrote it as a linear combination of two solutions. So x and x e to the power ix 1 by x is the other two solution. Yeah. So one last thing, like we could write this using the superposition principle. Since the differential equation was linear, so we could write this as a linear combination. So that would also represent a solution of my differential equation. So that's all for today's class. So in case if you have any doubt regarding this lesson, you can ask me right now, or yeah, if no doubt, let's end today's session and meet in the next class. Okay. Let me stop the recording now.